Morning everybody, Lenny Reed, Dynomite Products. Matt says I've got 30 minutes because after that I get boring. So I'm gonna opportune the next 29 minutes and 30 seconds to give you guys some knowledge on cold start, drivability, throttle response, fuel economy, horsepower, atomization, spray angles, different patterns, a lot of stuff, so pay attention. So first off, we're gonna talk about some, I get this question asked a lot. So when the 12 valve trucks come out, they come out with a 145-degree spray angle, and a 155-degree spray angle was actually in the marine application, but the P570 and the P665 nozzle was bigger and it made more power. So what we did is we actually just used a thinner copper. We would drop the injector down into the cylinder head a little bit deeper to get our protrusion or nozzle protrusion into the combustion area better, and we kind of made up for the angle by doing that, and it worked really good. So to this date, I have bought a bunch of cool tools, and I'm not smart enough to use them, not all of them. So, but there's people in this building that can, and they tell me stuff. So what I've learned is a P570, which would be the marine style nozzle, if we're gonna measure the angles, those are on an elliptical style pattern, meaning that it's kind of tilted. And the reason it's tilted is because the injector sits to the exhaust side of the head and it kind of points in towards the piston bowl. And the piston bowl is offset. So this is my replication via hand and expo marker of what a 12 valve piston bowl would look like. It's really small diameter, it's offset, and we've got a nozzle that's coming in at a 20-degree angle to get all of the spray holes in that bowl. Now on a 145 degree, which is what that nozzle came from the original, like from Dodge, it came with a 145 degree. Well, since they're elliptical, the holes all don't use the exact same angle. So what they use is, and we measured this here this morning, 73.5 degrees, 83.3 quarters, 73, 63 and 3/4, 63 and 1/4. That gives us a total of 357 degrees of angle. Then we divide that by 5 because there's 5 spray holes. That gives us a total of 71.45. Let's call that like 71.5. We multiply that times 2 because this is the total of half of the nozzle. Multiply that times 2 and we come out with 142.9 degrees. So if this, like if I fudged on this by a little bit and that was 71.5, this would be 143, 144 degrees of spray angle. Bosch calls this a 145. So depending on how I fitted my wire in there and how accurate I was with the angle, or even how accurate they were with the angle, this is a 145 degree spray pattern using those different spray angles to get it into this style bowl. Now the P570 is a bowl that's larger in diameter. It's still offset. You've still got the injector coming in at a 20-degree spray angle, but the degrees of angle are a little bit different. We got 68, 89, 88.5, 68, 68.5, grand total of 382, divided by 5 again for 5 spray holes, ends up with 76.4 times 2, 152.8. Bosch labels that a 155 degree spray pattern. So again, depending on how close I was getting all of my wire to fit in there, that could very well be 155 degrees exactly, or it might be 153 degrees. Now, with the OEMs, if I was to take 6 of these nozzles and measure all of them, they would all be a little bit off because that wire doesn't really, it's not exact precise. We're talking about, you know, thousandths of an inch with a little bit of deviation, but generally speaking, it is a 10-degree spray pattern difference. Now, throughout the years, like I say, we've learned tricks on nozzle protrusion, how to get that thing into the bowl a little bit better, and since it's a low pressure injection system, the spray holes have to be fairly big or they don't shove a lot of fluid very far into the pocket of the bowl. So by dropping this nozzle tip down into the bowl, my protrusion is closer to the bowl and we're getting to more oxygen and it makes more power. So for everybody that wants to argue about 145 to 155, blah, 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 blah. The spray degrees are not that drastic. But this is an actual fact. I just wanted to share that with you. So now we're going to move on to a little bit different style discussion. If I don't lose a finger with that thing. It's got a really stout little spring on it. Okay. I want to talk to you about different style nozzles. A moment ago we were talking about the elliptical stuff. So we've got a piston bowl and we've got an injector that's coming in from the offset. So that has to be elliptical. When you look at them, it's going to kind of go down and around and back up as you rotate that around in front of your hands. When you've got a dual plane, that means we have holes that are set up. If I do this very quickly, we got one low hole, we got one high hole, we got a high hole, and then down around the corner we're going to have another low hole, dual plane. So we've got, oh, call it 20 thousandths difference in elevation right there. And they did that whenever they were running out of room, so they couldn't fit it all on a flat plane. Flat plane is going to be same concept, hole, 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 flat plane. When you look at the outside of the nozzle, you never run out of room. Physically, those wires are coming into a smaller area. So when you get inside and you use the borescope and you look in there, you'll see those holes they're getting very close to colliding, and that's not good. So they had to use the dual plane on certain applications to try and keep the strength and the integrity of the nozzle up. Now, we've talked about dual plane, talked about elliptical, talked about flat plane. Pilot. Pilot is something that we've designed here, and basically what we've discovered is if we have a nozzle, and let's say that we're working on a flat plane just for ease of drawing, I'm going to say that these holes are 10, 12, 14 thousandths of an inch on the outside. So when I measure this area right here, let's just say it's 10. My pilot hole is going to be installed at a different level, closer to the combustion process. And what's going to happen is these holes are going to be about 50% whatever the primary hole size was. And the reason for that is because at idle, that's your lowest injection pressure. The atomization is going to be the worst. Fluid is really cool because it always wants to go the path of least resistance. The pilot holes at 50%, all they do is they use that very low injection pressure to help atomize and start the burn. So a lot of our technology now that we're using has pilot holes involved in it because this fluid is going to come out and it's going to travel about yay far. That's when it's going to finally ignite. My piston is going to be like here, my piston bowl I should say. It's going to be here, and we want to use up as much oxygen in this area as possible. That's how you get the most horsepower out of that bang. Well, when your atomization is poor because you've got low idle pressure, you end up with idle haze, cold start issues, things like that. Now when I put this hole at a little bit closer to the pocket, this fluid is going to be atomized much better, and it's only going to travel about that far before the finer atomized particles of fuel take ignition. The moment that takes ignition, we're going to get a very small spike in cylinder pressure. That's going to increase the temperature in the combustion bowl, and you're going to get this stuff to light more completely. At wide open throttle, what will happen is basically path of least resistance kicks in, and the fluid is going to go out the bigger holes because it's way more convenient for fluid to go out bigger holes than it is smaller holes. So at that point, the pilots aren't really contributing to the horsepower of the engine. That's still going to rely on the big holes. But we, with the pilot holes, have tried to use some of these older mechanical injection systems, P pumps, VE pumps, even VP44, to try and enhance that cold start and that just the tip in right off the very bottom end. With a mechanical style truck, they can be a bit smoky and such. When we enhance that burn just off the bottom, they become a lot more crispy and a lot more just throttle responsive in general. So now that we've talked about all of these things, we're going to talk about angle. So every single piston has an angle that, that the factory is basically optimized. We talk about that in say 155 degrees. 155 is not 100, so that's not 155 degrees of spray angle. That's actually half of that, because I've got 155 degree difference between the two. So I'm going to be 155 divided by 2, 75 plus 5, 2.5, 57, 77.5. I think that's correct. So 155 divided by 2 equals 77.5. So 155 degree spray pattern is from the center point at 90 over 77.5 degrees. Now, why that's critical is because with every single piston, if you're off by 2 degrees, you're only off by a degree per side. So we're only off by 1 degree here, 1 degree there, 2 degrees total. When we're trying to do things as fast as we're trying to do things with common rail, remember that common rail doesn't just have one injection event. It's got like an emissions event, it's got a pre-injection event for a pilot, it's got your main injection event, and then it may have a total of 7 injector events during each combustion process. So the OEM knew what the crank throw was, they knew what the dwell time was going to be, and they factored that into all the tuning. So if we're off by a couple degrees, 4 degrees makes a real mess. 4 degrees, the truck will start, the truck will run. It's not going to be the most throttle responsive. The exhaust gas temperature is going to be higher than it should be in any given point in the throttle. Smoke control is going to be worse. Cold start ability can be very atrocious. So when you buy a nozzle that's say 128 degree spray angle, but your piston was designed for 124, you're off by a couple degrees per side, it'll start, it'll run. And if it's a big nozzle, it'll make more power than your 124 degree nozzle, but it won't do it all correctly. It's never going to get the proper fuel economy. Exhaust gas temperature is always going to be a fight. The throttle response is going to feel lethargic, even though when you finally get down on it, it'll make more horsepower. So you're kind of compromising by not using the correct spray angle. Tuners have the ability to manipulate injector timing, and that can help with some of that spray angle, but mechanically, they cannot fix the wrong spray angle. That's something that when we do the EDM, with EDM, I basically have these little tiny sticks, and this is a consumable part. We dribble water over this, so as the water dribbles over this rod, this is a 0.0052 wire. So a little bit bigger than the human hair. The average human hair is about 3/1000ths of an inch. When I dribble water over this at 100 megohms resistance and I charge this wire, it basically hyper fast rusts its way through the nozzle, and it does it in a way that doesn't use enough heat because the water is dissipating the heat. This part never actually touches the nozzle, it's the water doing all the cutting. So it's a really nice, clean, safe process. The tools that we own for this, extremely accurate. The programming is all something that gets wrote inside in the house. So not all EDMers are going to be the exact same quality because tool technology, and because of the guys doing the programming and how much research, how much time they really want to hone in on the CNC programming of that machine. With wire diameter, we're learning a lot. So just to help me, because I'm old, we've got one wire here at 0061, so 6 thou 1/10. I've got another wire here at 0055, so 5 thou 5/10. I've got another one at 0050. So between these two wires, there's 1/2 of a thousandth inch in diameter. Now, if it was only one hole, there'd be almost no measurable flow difference. But since you've got 5, 6, 7 holes, now you've got to multiply that little tiny amount of flow by 5, 6, or 7, and there is a flow difference. So next on the hit list, I grabbed some 4/0 wire, and I grabbed some 5/2. So 4/0, very, very small, a little bit bigger than the human hair. We've got 5/0, we've got 5/5, and a 5/2. These 3 sticks of wire are responsible for every hole that's ever been made by anybody in the OEM industry. They're all going to use EDM because it's most accurate, it's most economical, it's the fastest way to process a hole. Now, 20 years ago, think I bought my Extrude Hone in 2004. I think it was January 4th, 2004 when I took possession of that. I was taking what was already done by the OEMs with whatever hole they've given me, and I was using Extrude Hone technology to process that hole and make that hole flow more and inevitably make more power. Now, what I didn't realize back then was by changing the shape of this hole, I was changing an awful lot of things, and there was no way for me to test them back then. We didn't have tools, didn't have the ideas, didn't have the knowledge, but we were doing what we said we were doing, which was making more power. Well, if you remember 2004, common rail was really new, very, very new. So LB7s, Cummins 5.9, pretty much the only common rail stuff that was on the streets at that point. Injection pressure was extremely high compared to a P-style pump. So we didn't have to manipulate those things very much to make 50 or 100 horsepower. And as common rail's grown, we're getting to be a lot better at it. Everybody from the engine guys, cylinder head guys, camshaft guys, injector guys, turbo guys, we're all getting better. So it's really critical that we keep stepping up the times and keep buying more tools that we can actually do things for very custom applications and do them correctly. With Extrude Hone, it's a very thick, pasty material, much like children's silly putty or Play-Doh. We force that through, and what it does, it takes a hole that's been EDM'd. So my wire would start out on the outside of the spray orifice, and it would burn its way in. This distance traveled, depending on the thickness of the nozzle, is going to be somewhere around 45 to maybe 55, 58 thousandths worth of depth that it goes into. So as I've traveled in my, say, 50 thousandths of depth, I'm going to leave just a little bit of the media that I just burned out of here. That steel kind of piles up right here, just on the outside edge of that hole. And it kind of looks like microscopic welding slag. So the first thing that we want to do is we want to knock that garbage out of there, because with this stuff there, as fluid is going to try and come around this corner at a 90-degree angle, that fluid doesn't want to flow over a 90-degree edge, especially when there's that little welding burr right there. So what would happen is if you EDM a nozzle only, and this is something that's very common that comes into the States, they're very inexpensive. You can buy garbage nozzles everywhere on eBay or whatever. You can buy stuff super cheap. EDM only, what's going to happen is this fluid is going to come around this corner. It's going to create like a little low pressure area. We're finally going to do this. Fluid's going to come around, finally going to do this. So you may be bragging to yourself and all your buddies that you've got some, say, 5x12s, because when you take a pin gauge or a drill bit or whatever you're doing in the backyard to measure these things, or you're just trusting that they're actually 12 thousandths of an inch, they're probably not. We've got really good gear here that measures stuff optically, and it's very accurate. Even though the outside spray orifice is 12 thousandths of an inch, by the time you've fed it through this low pressure area right here, you're feeding that with maybe 6 or 7 or 8 thousandths of an inch. So the pressure coming down this direction is very, very low. You get lots of smoke, and you don't end up with the kind of quantity coming out that nozzle that you should have. Fast forward to Extrude Hone 20 years ago, we would get rid of this 90-degree edge. We would abrasive flow machine with Extrude Hone, and we would make that hole very, very effective. We were getting a lot more. If this is 12 thousandths, our flow compared to their flow was way greater than. We were getting 12, 13 thousandths holes to party and contribute like other guys with 18s and 20s. Problem is this. This is supposed to be set at an exact angle, aiming towards the piston bowl. Well, by doing this, we've semi-destroyed the angle, and we've turned it into kind of a sawed-off shotgun blast. So if this is pointed at 73 degrees, and I've diminished a bunch of that guide, I'm no longer a rifle aiming that, I'm more of a sawed-off shotgun aiming that. So I'm getting it in the bowl, I'm not outside the bowl, or am I? We didn't really know. We're going to fast forward to abrasive flow machining. Now, AFM is a very, very water, or almost even like a paint thinner kind of a substance. Very fluid, has no viscosity to it whatsoever. You run the stuff through at a much lower pressure than Extrude Hone. The cutting agent that's in it is not near as aggressive as what's in the Extrude Hone, and it's the only way to process anything that the OEMs are kicking out to us today. And by what I mean by that is all of the OEM stuff, back in the day, a P570, for example, on the back side of that is a 5-hole at about 12.7 to 12.9 thousandths of an inch. So a fairly good sized hole. VP44, I just recently measured this so I remember it. It's the RV275 horse nozzle is 7 holes, 153 degree spray pattern, and those holes are like 9.8, 9.9 to 10 thousandths of an inch. So with the gear we have, we can roll the nozzle around and measure all those holes, and we just take the overall average, because all 7 holes won't be the exact when you're measuring that many decimal points over. But let's say it's a 7 by 10. Let's get into common rail stuff. Like today's common rail technology with ultra high pressures, 32, 33, 34,000, we're gonna see holes that are down around like 6 thousandths, 5 thousandths of an inch. And after they AFM those, they flow quite a bit. But with that big pressure, you'll see a factory power stroke come out right now, 450 horsepower using a hole diameter that's less than 50% of a power stroke that made half the power. So it's the added pressure that's really giving them the quantity and the extra accuracy. Like the injection event, the tuning, the ECM, it's all just a lot faster. Piston goes up, piston goes down. What you do at the very top is hypercritical these days. AFM became necessary for us. We had EDM, we had Extrude Hone. We knew there was a limitation because we've got customers, GSL, great guys, great customer. They're in Australia. Those guys are sending us stuff out of engines over there that are much, much smaller. So the Toyota Hilux, high pressure common rail, but the spray orifice was brutal to get Extrude Hone through. Every single time we would try an Extrude Hone, 1 or 2 or 3 of those holes would plug with the Extrude Hone media. So then we're trying to shove a 3/1000 pin gauge into that hole to knock that plug out of there, clean it out, and then we would try and reprocess it again. So because of GSL using the Toyota Hilux motor, high pressure, very small, it gave us the fast forward momentum to start thinking like what's gonna happen in America to all of the manufacturers that we're dealing with now. We've got smaller Duramaxes coming out, we got smaller Power Strokes coming out, we got the Eco Diesels coming out. Those motors use smaller spray holes inevitably because they're making less power. But now with the really high pressure stuff of the new Power Stroke, we're using very small holes. The only way that we can treat those is not with Extrude Hone. You certainly can't rechase them with EDM because with that much pressure, by the time you try and rechase it, the hole's way too big. So we're left with just AFM and adding pilots to it. Now, trying to stay within like what I'm really wanting to talk about here. A lot of our stuff that we were doing 20 years ago, these trucks were a little bit unpleasant and unbearable to drive. Recently, we've got a brand new dyno, we've got gas testing equipment, we've got the opacity test equipment, and from 3 thousandths to 7 thousandths, I've got this many pieces of wire to choose from, and in the bottom, there's a bunch of miscellaneous pieces. So from 3 thou to 7 thou, I've got so many different ways to create a hole. Then I come in and I start processing them with either Extrude Hone or AFM. Why do we still use Extrude Hone? Everything that's about 9 thousandths or larger in hole diameter gives us a really nice K factor without having to blow it open like that. Anything that's say 8.5 thou or smaller, we use AFM. We're having to use different pressures with AFM and Extrude Hone to get the radius that we're after. This picture of this AFM radius is exactly like when we're looking at the bore scope, that's the kind of thing that we're wanting to see. We're basically looking for an EDM'd hole with about 10 to 13 thousandths flow increase, and that gives us the proper radius. That is like mint. Atomization is so good, the startability is good, the mileage is good, we've got really good control over our spray angle. Now, this morning it was 5 degrees here in northern Idaho. I pushed remote start. Waited for my 1997 12 valve with the hot rod, like quick rate injection cam. It's a little bit, the backside of the lobe is so aggressive that it doesn't like to idle very well at all. But when you start giving it the beans, it really starts to rip. This truck with remote start, 5 degrees outside. I posted a video this morning. We're going to post that video, just a brief moment of it in this video as well, so you can see it. Proper holes, treated correctly, 12 valve, static timing, starts great, works great, it's awesome, love it. We're going to also post in this video what we've been working on was a project with Calibrated Power Solutions, Diesel Power Products. They had a Hamilton cam, they had some BD twins, basically a stock like 06, 07, 59 truck. Has a catalytic converter still on it and a full exhaust system. We got that truck to make a smoke-free 700 horsepower. It's amazing. Throttle response is super crispy, very fun to drive. It's got 38-inch tall tires, 4, 5, 6 gears. It's a dream. Like, it was so much fun driving it back to those guys. From my dyno out to their shops, about 60 minutes. Ton of fun to drive. We spent, the guys at Calibrated haven't really done a lot of our stuff and tuned a lot of our stuff, and our stuff does not tune like everybody else's. So it was really amazing for me to be able to give them the air-fuel ratio, a video of the smoke. We would record boost and drive pressure and exhaust gas temperature. All of that stuff will be in this video, and we'll show you clips of that as well. Because with all of these technologies assembled to our company, we're now able to do things that are just way more professional, way more accurate than we've ever been able to do it. Wow, I hope we get to cut that out. That was bad. I'm not even drinking yet. Anyways, so it's almost the end of the video. I hope this helps. I hope this makes you understand things a little bit better. Technology in 2022 is not the same as it was in 2000. It's not the same as it was in 2010. It's not the same as it was in 2018. We have gotten so much better. And we're doing that to make your guys' old trucks run like the new trucks without the $100,000 price sticker. So anyway, Lenny Reed, Dynomite Diesel Products. Have a good weekend. Thanks.